Tēnā koutou, no mai haere mai ke tēnei kōrero, ko Pete Russell Takawingwa no Ngāpuhi ahau. Kia ora, I'm Pete Russell, I whakapapa back to Ngāpuhi up in the North Island. I grew up in Whanganui and I've been living in Dunedin for the last 20 years. I live out at a beautiful place called Karatani, which is about half an hour north of Dunedin. Okay, I've got quite a few slides to get through, so I'm going to do the first part quite quickly. It's quite educational. And we'll get to the end part. So the title of my talk is Haumātakataka, which just translates to cyclones. Okay, and I'm looking at a cyclone bloom that we had about 18 months ago following Cyclone Oma in the Pacific near Vanuatu. I'd like to acknowledge my main funder is Te Koranga, which is the Indigenous Science Research theme here at the university, but also the various other resources that I access. So when I was teaching in marine science, I used to tell my students that you could do oceanography with no money. It was just other people's money, mainly American money. I'd also like to acknowledge in the time that my research covered, which is the last 21 years, the impact that it's actually had on people in the Pacific Islands and just the loss of life that these cyclones cause, and also the huge amount of damage. And even this year alone, just with Cyclone Harold, there were 34 lives lost in the Pacific. Okay, just a bit of background. About half the tropical ocean is desert. So it's desert. All the nutrients have been used up through photosynthesis. Okay, nutrients need, marine plants, need nutrients to photosynthesize. Okay, and tiny marine plants called phytoplankton use them as well. And then smaller organisms called zooplankton eat the phytoplankton. Then you get bait fish eating the zooplankton all the way up to pelagic species like tuna and jaws. So below the warm water, this is what we call a thermocline, nutrients actually get trapped below this thermocline, and that's very much the case in the tropical ocean, unless there's something that could break the thermocline like a coastline, for example. Okay, so it's quite dark deep down below the thermocline, so you don't get photosynthesis happening, and that's where the nutrients are trapped. So my talk is based around that. Storm chasing, when people think of storm chasing, they think of all these vehicles tearing around the Midwest. Okay, this is storm chasing Pete Russell style, just on a computer with an internet connection and accessing various different websites that are funded by various agencies throughout the world. Okay, tropical storm systems, and before I started looking at this, there was a lot I didn't actually know. I thought they were in the tropics, but actually there's a big band around the equator that you don't get these big tropical storm systems, and that's due to Coriolis. So Coriolis is a major player in tropical storms. My best way of describing Coriolis is if I'm on the equator and I throw a ball to us here in New Zealand, okay, it's got quite a fast east-west speed. So if you're on the equator, you're going really fast round and round the world every 24 hours. Okay, if you're at Oamaru, which is halfway between the equator and the pole, you're only traveling half as fast. So when you throw that ball, it retains that east-west speed. And I throw it all the way to Oamaru, and it's going much faster than the air is moving at Oamaru. So it has an effect of bending towards the left, okay? It's sort of an effect, and that's probably my best explanation at Coriolis, okay? It retains that east-west speed, and this is why fluids, when they move across the surface of the Earth, do things like bend to the left in the southern hemisphere and bend to the right in the northern hemisphere. So the reason why we have no tropical cyclones near the equator is it gets confused. It goes, oh, am I supposed to be going to the left or the right? Okay, as it's crossing from the north to the south. So that's probably the best I can do with that explanation. Okay, so these are the main areas in yellow where you get cyclones forming. probably 60% of cyclones get formed here in the Western North Pacific, which is called the Western Pacific Warm Pool. Okay. Not a lot of work's been done in the South Pacific, but that's another major ocean basin. And you need certain conditions, like you need the water to be at least 26 degrees down to about 50 meters. So these storms are powered by warm water. Okay. Storms have different categories. There are various different scales. Australians got one. This is one that the Americans use, okay, and I tend to follow this one. And category 1, you've got these ones read all the way up to a category 5 storm. Okay, they get stronger and stronger. Storms are powered by latent heat. Okay, they tell me a steam burn is a lot worse than water at 100 degrees. I've never tried it, but you get a steam burn. Evidently it imparts a lot of that latent heat when it condenses on your skin. And tropical storms work the same way. So the sun evaporates water from the ocean. That in turn forms clouds, and they rise and they start to rain. So when they precipitate out, okay, they release a lot of heat. That heat in turn rises further. That brings in more and more warm, moist air, and so on and so on. So it's a bit like a fire. You've got this fire and you're continually throwing fuel in it, and it just keeps on getting more and more fuel. And once you combine Coriolis in with that, it takes on a life of its own. And it would keep on going indefinitely if it didn't hit places like land or move down out of the tropics, okay? So some storms have literally gone all the way from the Eastern Pacific all the way across the Pacific and power themselves that way. But once they hit land, they're losing that force. Okay, so the final concept we're going to have a look at is Ekman transport. So it's again related to Coriolis. So when wind blows across the surface of the ocean, it moves that top layer. Okay, but due to Coriolis, that top layer in the southern hemisphere wants to start moving towards the left as it moves, and in the northern hemisphere it starts wanting to move towards the right, and then that moves the bottom layer, and so on and so on, and you get this sort of spiral of, say, in the northern hemisphere wanting to move towards the right. So Mr. Ekman, or Dr. Ekman, was up in the northern, somewhere near the North Pole, and he was watching the wind blow one way, and all the icebergs were moving at right angles to the direction of the wind. Okay, and that's how he came up with this net transport to the right. So when the wind blows across water, the net movement of water, the surface layer might be just moving towards the right, but if you take that all the way down for the influence of the wind, okay, your net movement of water is towards the right of the wind at right angles. And in the southern hemisphere, it's towards the left. So what that means is when a tropical storm starts spiraling on top of the ocean like that, okay, it actually makes the water diverge away from the center of the storm. So all that water, this is a southern hemisphere storm, okay, it's circulating clockwise, that water diverges away. So what that does is move that surface water away from the center of the storm, and that causes water, deep water to upwell near the center of the storm. Of course, if the storm's moving too fast, it won't do this, okay? It won't have enough time to get that water moving en masse. So that's sort of the main area of my talk. So if we look at Cyclone Gita a couple of years ago, this had a big effect on Tonga. It went straight through Tonga as a category 4 storm. Okay, if we look at the path of Gita, here it comes round past Tonga, below Fiji. Okay, so this is a temperature anomaly. This is the sea surface temperature anomaly, a departure from the normal sea surface temperature, and it's really lowered the water temperature by about 3 degrees. So in the wake of the storm, you can see a cold water trail. Okay. There's a real deep area here. This is, I think it gets down to about 4 degrees here. That's some really cold water that's been upwelled. So there we may see what's called an increased level in chlorophyll concentration. This is small marine plants. Okay, so there's a slight increase in chlorophyll in that area. This is not what I call a huge increase, but it's brought it up enough nutrient-rich water for photosynthesis to happen, okay, in that location. And that's quite a big location, okay? For every degree, you're looking at, I don't know, about 80 kilometers or something like that, okay? It wasn't huge. The thermocline's quite deep there, so it has to do a lot of this spinning to get that water to upwell, okay? Cyclone Oma did this really well, and when I look at this is what we call, these are called fixes, 6-hourly fixes of the storm. When I see something like this, I home in it straight away and go, yeah, that's going to cause a huge bloom. So this is Oma, okay, there's the sea surface temperature response, okay, it lowered that temperature. This is a phytoplankton bloom, and it's huge. It's the biggest one we've had in the Pacific in 21 years, okay. The storm wasn't particularly big, it was category 1. The thermocline is about 80 meters, okay, but to give you an idea of the size of this, okay, here's New Zealand here, so it's roughly the size of Otago, that bloom, okay, so that's a lot of green stuff, that's a lot of productivity. So here's a summary of some of the storms that we've had over the last 21 years, and about 13 of them have produced really noticeable blooms like that. So I didn't count Gita, that wasn't what you call noticeable. Okay, what am I doing here? Okay, so when we look at what causes it, when a storm slows down slow enough, that'll cause a really good bloom. So it's what we call translation speed. So I got a thing called hover, which is the inverse of translation speed. Instead of meters a second, it's seconds per meter, the time it takes to travel 1 meter. Okay, and Oma had a very high hover speed, so it hovered over one area for long enough. Okay, and if I take all the storms and look at this hover parameter, okay, it produces a fairly good plot. And these are the storms from the Pacific. Okay, there's a few outliers, but it's also very difficult to actually quantify this information. You're trying to get stuff from cloud-free days from satellite images. Okay, so this gives you an idea of the size of this, and here's Oma here. Okay, there are other factors. That's the main bloom that it upwelled, but also all that rain onto the islands as well causes runoff from the land, and that also causes a phytoplankton bloom as well. Okay, and so that's the main bloom, and that's runoff from the land. So it happens quite quickly and it disappears quite quickly. So my main questions there is, we know this happens. What actually happens to this stuff? Does this support a regional fishery? You know, does this support a food chain? Does this get eaten? With the climate change size of it, okay, does all that productivity, if it doesn't get eaten or get into food chains, does that actually sink down and form part of a geologic layer? Because if it does, okay, this could really help predict future storm activity. So if we have a look at the picture that Chris Moy showed earlier on, or a similar picture, if we look at the last interglacial, which is what we're sort of heading into now with increasing sea temperatures, okay, if we could get sediment cores, because that bloom process is quite a random process, over 20 years we've only got 13 of them. One of them's been really big, so you might only get a big one maybe every 20 years. Could you see that in the sediment? And if you can see that in the sediments, then we can start relating that to sea temperature rise, and then at least we can sort of say to Pacific nations in particular, you can expect this level of storm activity over the next 100 years. They have done that to a certain extent, you know, with looking at storms in general. Okay, so this is probably the first really good paper that's come out and said we are getting stronger storms. Okay, and that only came out this year in PNAS. Okay, and these are what we call fixes, those 6-hour dots. And this is the percentage of fixes that are category 3 to 5 of all storms. So this is 40 years of data across all the ocean basins. okay? And so we're getting a 25% increase in strong storms over the last 40 years. So it's probably the first publication that's come out that said, yes, we are getting that increase. Once we can start relating that to increases in sea temperatures, then we're going to have the ability to say, yes, you can expect more. There is a limit though. You're not going to get 100 category 5s in an ocean basin within a cyclone season. The reason being is these things take up space and time. Okay, but the storms that you do get, perhaps you can expect them to be a lot more powerful. Okay, I think, yeah, that's us. Yeah, any questions?